Hello, everyone. My name is Abu Bakr Abid. I'm a fifth year PhD student at Stanford University. I'll be presenting Meaningfully Explaining a Model's Mistakes, which is a paper that I wrote with my advisor, Professor James Zoe. So let's start with some motivation. So imagine a pathologist who downloads a pre-trained model to classify histopathology images like the images shown here. Now, this is very commonly done. You download pre-trained models all the time. But despite having a high reported accuracy, the pathologist finds this model is not working well. Okay. So when a model isn't working well, there can be lots of different reasons. For example, imagine that the pathologist finds that the hues in these images are different than in the original training data. Okay, this can happen because pathology images have different dyes or different stains. And after he realizes that this is the issue, he simply pre-processes his own images and then matching the training distribution and thus recovering the model's performance on his or her own images. As a second example, imagine a dermatologist who trains machine learning classifiers to classify skin diseases from skin images like these. Now, when the dermatologist she shares her trained model with a colleague from a different hospital, the model's performance decreases. The model is making lots of mistakes. So she investigates why the model is making these mistakes, realizing that the patients at her colleagues' hospitals have different skin colors and ages and so on. And so understanding why a model's performance degrades during development or deployment can help you actually build more robust models or get a model that's pre-trained, get that to work on your data. And so the goal of our method is to be able to automatically explain why a model is making mistakes. And so the output of our method, it looks something like this. So on the left here, we actually have the input to the method, which is an image that's been misclassified. So the inputs of our method is some sort of misclassified sample. In this case, it's an image of a zebra that an image classifier, a standard InceptionNet type image classifier, it classifies this as an African hunting dog. The output of our method is, first of all, it tells you what concepts, in human understandable terms, what concepts are missing from this image that would increase the probability that this is correctly classified. So in other words, this is misclassified because it does not have stripes. Okay. And then in this case here, so for example, you have this image of a couple of zebras, that's being misclassified as an African crocodile, even though zebras are the dominant images here. And so we can understand that if the zebras were present in field and the water wasn't present in the image, then it would be correctly classified. Okay, so we can understand how these concepts explain the misclassified sample, and then we can also see in kind of a map what are the different concepts and the relationship between different concepts that explain why the model is being misclassified. So we can see this kind of in a more holistic way, that a bunch of concepts like are about that relate to land that are missing from this image that explain why it's not being classified as a zebra. And a bunch of water-related concepts are present in the image, which are causing it to be considered an African crocodile. So how does our method work? So we actually build off of two pre-existing methods, counterfactual explanations and concept activation vectors. So counterfactual explanations perturb images or perturb different samples and try to change the model's prediction. Concept activation vectors are ways to actually learn concepts in a bottleneck layer of a machine learning classifier, and they provide a way to actually understand how a machine learning network, how a neural network understands human interpretable concepts. So we combine these two ideas and introduce some of our own to actually develop this idea of a conceptual explanation score, or CES. And so the way it works is we do perturbations similar to counterfactuals, but we do it in the concept space. So in other words, we try to understand what concepts can we add or remove from this image that correctly then cause it to be classified. So we start off by learning a large set of concepts. In our papers, we start with 160 concepts that we learn with varying degrees of success. These concepts include things like settings, so bedroom, street, landscape versus ocean. It can include the absence or presence of objects such as basket or apron or bed. It can also include things like textures, And finally, it can also include things that are kind of like low-level image qualities, such as blueness, how much blueness there is in the image. Okay, and so we can validate CES in a number of different ways, and we do this in the paper. For example, one of the things we do is we take an image that is correctly classified, like this image of an apple, and we actually slowly turn it grayscale. So we start off with apple being correctly classified. You can see the probability of it being understood as a Granny Smith apple is nearly 100%. But then as we slowly turn it more and more gray, the model loses confidence. And this is a standard off-the-shelf image classification network. It loses confidence, and the probability of being correctly classified goes down. And it classifies it as like a mortar. And so at the same time, we run CES to understand why is it being misclassified, and we see that the probability of it being the explanation that our method gives is that it's not green enough. If it was greener, then it would be correctly classified as a Granny Smith apple. So this matches our intuition. This matches the perturbations that we're doing in these models. And we can repeat this experiment with many different images, finding consistent results. Another thing that we can do is we can actually train spurious models. So what we do is train these neural networks to classify images, but in our data set, we introduce these spurious correlations. So for example, all of the images of dogs include snow somewhere in the image. And we use a data set called the metadata sets to construct these data sets for spurious correlations. We train our model, and then we introduce an image of a dog without snow. And we ask our model to explain why is this not being classified as a dog? And what we find is when we look at the top 3 conceptual explanations that our method provides, very often it correctly says that, okay, the reason it's not being classified as a dog is because there's no snow in the image. And this is pretty cool because with a single test example, we can learn a spurious correlation that our model has learned. Okay, and we find, for example, here that in 100% we test 50 different images, in every single one, if I just introduce that, snow is one of the top 3 conceptual explanations. And I can repeat this with many different spurious correlations that I introduce in my model, and I get the results with varying degrees of accuracy. So there are some cases where concepts may be a little bit more heterogeneous, where our method doesn't work as well with a single test image. So for example, when dog is correlated with horse, it turns out that our conceptual explanation scores only recover this about 24% of the time with a single test image. However, even in this case, we can batch together multiple misclassified images. And for example, if we have 5 misclassified images of dogs and we batch them together, then we recover at least 90% performance in those groups or in those batches. Horse is correctly identified as the missing concept as one of the top 3 conceptual explanations. So we have a lot more results, a lot more explanation in our paper. If you are interested, check out Meaningfully Explaining a Model's Mistakes. It's in the ICML workshop on theoretic foundations, criticism, and application trends of explainable AI. Thank you so much for listening, and we look forward to hearing your feedback on our work.